Hello, everyone, and welcome to this next video on machine design. We have come a bit. We started looking at the design of shafts, okay, on the basis of strength. Remember that you can design shafts based on strength, or you can design them based on rigidity, okay, rigidity. But we have been looking at the design of shafts based on strength, and we looked at a few cases. The first case was the case of a shaft that is subjected to torsional moments only, and we did derive these equations, okay, for shafts that are subjected to torsional moments only. And the assumption there is that the bending moments are zero. So what that means is that the transmission elements, gears, pulleys, and the rest that are mounted on that shaft have negligible weights, right? And so they do not cause any bending moments in the shaft. Equation 5, as derived, was for solid shafts, and then equation 8 was for hollow shafts, okay, where d sub naught was the diameter, or the outside diameter of the shaft, right? And then we, of course, derive these equations. We use them time and time again. Supposing we know the power to be transmitted in the shaft, then we can know the torque transmitted and through that relation there, the equation. And in the case of belt and pulley systems, or belt and pulley drives, if you know the tension in the tight side and the tension in the slack side, and you know the radius of the pulley that runs that belt, then the torque being transferred is given by equation 11. And then we move to the second scenario where we had a case of an axle, because we said when you have a member that that's only subjected to bending moments, it does not turn, it does not rotate, we do not call them shafts. They are technically called axles, right? But for the sake of our calculation, we consider them as a case of shafts that do not rotate, okay? So they are subjected to bending moments only and not to torsional moments. And we derived these equations for them. So these are the equations that govern or help us decide or determine the diameter of the shaft, solid shaft, when they are subjected to only bending moments and not torsional moments. Equation 17 deals with hollow shafts that are subjected to bending moments only. And then we now introduced a case which is a more realistic case, where we have combined bending moments and shear stress. So that's the case where you have the transmission elements mounted on your shaft. They have significant weights, and as a result, they develop or they initiate bending moments in the shaft, and at the same time, the shaft rotates to transmit power. Okay, so in that case, we saw two theories for determining what goes on in the shaft. The first theory was the maximum shear stress theory, okay, or the Guest's theory, where we said that there was an equivalent twisting moment. Okay, so we know that there are bending moments and there are torsional or twisting moments occurring in the shaft, but we assume that it's just a case of it's a shear stress case, okay, a case of only torsional moments. But we now find the equivalent torsional moments, which will be a factor of both the bending moments in the shaft and the torque to be transmitted. Okay, so we had this equation 20, that said the equivalent torque, okay, transmitted in the shaft is given by this, the square root of the sum of the squares of the maximum bending moment occurring in the shaft and the torque to be transmitted, right? And then that equates to that, which is very similar to the right-hand side of equation 5. Remember, we are saying, okay, this one said only torsional moments, and that was the equation that related this to the torsional moments. But this time around, we have bending moments as well, but we have now gotten the equivalent, okay, and we define this as that torque that when acting has the same effect, right, as these two guys acting combined, right? And then the second case is simply the case of this for a solid shaft, and equation 24 is for the hollow shaft, okay? And we know how to relate the diameter of the solid shaft to the outside diameter of the hollow shaft, and where K is a ratio of the inside diameter to outside diameter of the hollow shaft. Okay. Then the second theory that helps us deal with the case of combined torsional and bending moments is the maximum normal stress theory, or the Rankine's theory, okay, where we treat the shaft as though it were subjected to bending moments only, but the maximum bending moment, we find an equivalent value for it, which combines the values of the maximum bending moment actually acting in the shaft and the torque to be transmitted. So we have this expression here that we say is the equivalent maximum bending moment, right? And then we equate that to the same thing we had in equation 14, right? We did that there. Maybe I should turn on my highlighter so you know where my cursor is at all times. Okay, I think that would be helpful. Great. That's the equation for finding the diameter of a shaft that has been subjected to both bending moments and torsional moments at the same time, but using the maximum normal stress theory, or the Rankine's theory. And this is the same for a hollow shaft. Now, in my last video, which was the last class we had on Zoom, we took one example that demonstrated this. The practice is when you have a case of combined bending moments and torsional moments acting in a shaft, we apply both theories. We apply the maximum shear stress theory, and then we also apply the maximum normal stress theory, and then we check which of them gives us the larger value, and we take the larger value as the safer value. Okay, so when we apply this theory in the last example, we apply this theory and apply this theory, and we had values there and here, and then we compared and selected the values that were bigger. So if I will go to my our calculation sheet in Word, just to reiterate what we did the last time. So we first of all applied the maximum. So this was the example, right? Our values were giving us straight, so we didn't have so much calculation. So we first applied the maximum shear stress theory. Okay, we from this, that's the equation there. If you make your diameter the subject of the formula, so we now went ahead and found the equivalent torsional moment, right, there, and then we plug that back into the equation with all the values that we had, and we found the diameter, okay, to 86.102 millimeters. And then we applied the Rankine's theory, or the maximum normal stress theory, which states that this is the same thing as this, because the square root of the sum of the squares of these two guys, we had evaluated that earlier on as the equivalent torsional moment. So we did know that value. And so all we had to do was to add that value to this, and then take or divide that by 2 to find the equivalent bending moment. And when you make your diameter the subject of formula, you would arrive at this. So we came on to evaluate the equivalent bending moment, and that's what we had. We took that, plugged it back into the equation, and then we found our diameter. So we decided to compare the Rankine theory, which is the maximum normal stress theory gave us a value of 83.72 millimeters. The maximum shear stress theory, or the Guest's theory, gave us a diameter of 86.102 millimeters, and our choice was to go with a larger diameter. That's the standard practice, right? And so we took that, but we had to select then which was the next highest standard diameter to this one, which was 90 millimeters, and that was the diameter of the shaft selected. We will do a different example. Just give me a minute to find it. Well, we'll do a different example now. So just walk with me through it very quickly. Hopefully this video, if it becomes too long, then we'll just do this example only, and then we'll come in the next video to continue with the next case, where we have combined bending moments, combined bending moments with torsional moments, but this time around with fluctuating loads. Okay, we'll come to that. What did we call this last example? This last example was example 4. So now we are doing example 5, right? So what do we have? It does say that a shaft supported by 2 bearings. Okay. We'll just keep that like that. Great. Okay. The shaft is supported by 2 bearings that are placed 1 meter apart. Okay, if you convert that to millimeters, that makes 1,000 millimeters, right? Now, a 600 millimeter diameter pulley, so the diameter of this pulley is 600 millimeters, right? It's mounted at a distance of 300 millimeters to the right of the left hand bearing. So you need to begin to create an image in your mind that describes what's happening. Okay, so if I would come down here, possibly I need to move to the next page, and I will let's use our shapes to see if we could get a sense of what is being said. So let's assume that this is our shaft. Okay, let that be our shaft, and this shaft is placed between 2 bearings. So let these be the bearings. I will give them a different color to maybe not that. Let's look at the feel. Let's give them, it's already blue. Well, light blue would be fine, or purple. Let's go with purple. Okay, we've got 1 bearing there, and let's have a different bearing. Usually when we're doing bearings, okay, let me tell you that we usually like for them to have lines. Already zoomed in a lot. We would like for them to have lines that cross them like so. Okay, one that way. All right, same line, and one that goes that way. Great. And I would want, let me group all of those so I can easily move them together. All right, now I need a second bearing. Okay, I need a second bearing. I think I can go back, reduce the size. So let me see everything. Great. I need this bearing on this side. And the question does tell us that this shaft is supported by 2 bearings that are placed 1 meter apart. So what that means is that the distance from this right hand bearing to this left hand bearing is 1 meter or 1,000 millimeters. We'll bring our dimensions in a little bit later. Just keep that in mind. And then it says that a 600 millimeter diameter pulley, okay, is mounted at a distance of 300 millimeters to the right of the left-hand bearing. So let's come down. This is the right-hand bearing. This is the left-hand bearing. So we're referring to this bearing. Now, we are going to move to the right of this left-hand bearings by 300 millimeters. So you need to estimate in your mind to know whereabouts that would be. If the distance from here to here is 1,000, so 300 may be somewhere around here. Okay, and that's where your pulley is. Now that pulley itself, when we're looking at it, is also going to have the shape of a rectangle like this, since we're looking at it from the front. Okay, I don't want that to be too big. Let's have it like that. Okay, let's color it something else. Let's make it ash. Bring it down a little bit so it's somewhere in the middle. So this bearing, the diameter means the distance from where my cursor is at the top to the distance, to the bottom. So that distance there is 600 millimeters, and it's placed 300 millimeters to the right of the left-hand bearing. Okay, I hope you are seeing how I'm extracting information from what is provided and creating my diagrams. Okay, and then it goes ahead to say that this drives a pulley directly below it with the help of a belt having maximum tension of this. Okay, so if I were, and I hope that my space will be enough for me to do what I need to do. No, it won't be. So what will I do? I'm going to have to make these a little bit smaller. I will convert this page layout. I will make it to be landscape from this point forward. Okay. Okay, so that I have more. You've taken my shaft all the way down. Okay, just bear with me. That's what happens when you teach digitally, use digital tools. There we go. So we come back here. We want that guy to be here. Right? Now, to avoid it moving around, I'm going to group that guy with this, and with that. That's already grouped, and with that. I thought I'd selected you already. Good. Now right click and group them. Okay. In that way, they don't move anyhow. So I'm going to zoom out a bit so we could see whereabouts we are. Oh, okay, so that's where I want the guy to be. Fine. So I got you from here. This is portrait. I wanted it to be here. Good. I wanted it to be in the landscape. So let me just bring this down. Now, what I will do now will be so that we can see what's going on. Is it now shift? Yeah. I want this to, let's lock the aspect ratio. Thank you. So that as I decrease it, it stays the perfect scene. Now the essence, what I'm trying to do is to make this the same size. So this is this pulley. I think that's fair enough. So if you look, and you are all engineers, so I shouldn't struggle with perspectives. Okay, I'll zoom, and yeah, let me leave that with that color. Give it a different color. let's make it light green. Excellent. So if you were to look at this shaft, so from let me look at it from this end. So let's assume that there's an arrow this way. Okay, that size is 0, and let's make it red just for illustration. And the arrow heads, no, I want that to be the largest. Crazy. Good. So assume that you look at this whole arrangement from the right hand side, the way we're looking, right? Then you would see this pulley. This here represents that pulley. Okay. There would also be, and I hope I've locked the aspect ratio. Yes, I have. There will also, you will see something that represents the shaft. Let me go on a little bit. I'm trying to make this as accurate as possible. You can't get it 100%, but let's try. And so that it's the same as the shaft. And let's move that to somewhere in the middle, roughly. Okay, so that's the shaft you will see. You probably would also see the bearing. Let's assume, but I'm not going to put the bearing in now. Just so let's zoom out a bit so we can see what's happening here. So the image you see on the right hand side here is looking at this whole arrangement from the right hand side in the direction that that arrow is pointing. So this small dot here represents the shaft, right? And this guy here represents this pulley, and the diameter of this pulley is 600 millimeters, right? Great. So the question tells us that this pulley that is 600 millimeters is it's delivering, where is it? What does it say? It drives a pulley directly below it with the help of a belt that has this maximum tension. So we have that if I would use arrows, then this pulley, right, is driving the belt down there. Okay, I think that arrow should have faced upwards. Give me a second. That's fine. I will make, I'll leave it that way. This should be 0. Yeah, because I want it to be perfectly vertical. So it's a pulley, and it's driving the belt system, so that you should have your tensioned arrows on both sides of. Okay, so we take this to the comma there, like so. Great. So we will call this, that's not very perfectly to the edge, so we will do to that better. We will give, let's select that so we can have access to, let's bring that here. Alternate tab to get our equations. That's going to be T underscore 1. Okay. Let's format that text box so that it has no line, but no fill as well. No fill. So this here is your first tension, okay? And I'm going to copy that and paste this, and this here will be the second tension. So the question tells us that the tight side has a tension a tension of 2.25 kilonewtons. Usually we take the T1, the first tension, to be the tension of the tight side. So this tension here is 2.25 kilonewtons. We have not been given the second tension. Okay, so at some point we will determine, so what is there any equation, okay, that will enable me to find the second tension if I know the first. That's why your exams in this in machine design is going to be open book. I'm not going to expect you guys to remember all the equations, but I expect you to know how to find the equations and how to apply them. Okay, so we try to mimic a real life scenario. You are doing a design, you are going to have access to standards, to handbooks, textbooks, and all of that. The question is, will you know what standard to use, what equation to use, where to find what value, and all of that? So this is not a stage where we're testing your memory. We're testing your ability to apply knowledge available to you to solve problems. Okay, so your exam is going to be open book, and you need to find. So you are looking at this question. You are given the tight side where the maximum tension is. So you need to know what the slack side is. Now, reasons being that if I know the tight side and the slack side, then I know the tension being transmitted. I mean I beg your pardon, not tension. Tension is what is occurring in the belt. You will know the torque being transmitted, because the torque will be a product of the difference between these two tensions and the diameter, the radius of this pulley. I showed you the equation at the beginning of this video. Fine, so we've read up until that point. We know the value of T1. We don't know what T2 is, but we do know that this pulley is driving another pulley directly below it. That's why these tensions are directed vertically downwards. Okay. Now then, let us now go ahead and read the next part of the equation, of the question rather. Then it says another pulley, 400 millimeters in diameter, is placed 200 this time around, 200 millimeters to the left of the right hand bearing, and this one is driven with the help of an electric motor and belt, which is placed horizontally to the right. Okay, so let's get our diagram again. And it's so important to have these things because they help you visualize. So you are seeing how I am translating the information I have from the question into this schematic diagram to help my understanding. Okay, so I'm going to copy and paste this pulley. The only difference is this is shorter. This one had a diameter of 600 millimeters, right? This one has a diameter of 400 millimeters according to the question. So I will reduce the height. I wish I did the math to know how to go down, but let's just reduce it to about 1.9 inches. 1.9, make that 1.9. Okay, let's assume that's 400, right? So let's centralize it over the shaft. Okay, that's 400. And this guy now appears 200 millimeters. Oh, yeah, I've gone too far. 200 millimeters to the left hand side of the right hand bearing. So this is our right hand bearing. We move towards the left. Okay, and it's a distance of 200 millimeters from that bearing. Okay, what else does the question say? 400 millimeters in diameter is placed 200 millimeters to the left of the right hand bearing and is driven with the help of an electric motor and belt, which is placed horizontally to the right. So for this second, so I'm going to have another copy and paste. This will let's reduce it. We actually want that to be about the same height as this guy. Yeah, thereabouts. Not a little bit more. Okay, and this one too should come down like so. Great, let's manage that. So bring that down a bit, and let's take it this way. I'll give it a different color so that we can easily see. We've had purple, we've had light green. Let's have light red, and we'll move it back. Okay, so that we can see. Yeah, it's about good. So move backwards. Send backwards. Send backwards again. Good. Oh, that's too far now. Okay, fine. Then we take this to the back. There we go. So you see me being keen to show, because if you are looking at this arrangement from the right hand side as it was designated by this arrow, then you would see the end of this shaft. I've deliberately not drawn the bearing, otherwise we'd have seen another circle there that represented the bearing. And then we will see this pulley, okay? And we will now see the outer part of this second pulley, because the second pulley is behind this first one if I'm looking at them from this direction, right? That's what you can see here. Now, this pulley, we are told, is driven by a motor that's placed to the right. Now, what that means is that there is going to be the arrow that shows us the tension acting in that direction. Okay, that's excellent. Like so. Okay, so we'll copy and paste, because that arrow is going to appear both up and down. Okay, let's see what that looks like. I need to bring it down a little bit more. Okay, there we go. There we go. So we will call, let's borrow you. Can I copy you and use you? Copy and paste. Yeah, and I'm going to move you here. Since we're numbering them 1, 2, let's call this one, let's assume that that's the tight side. Let's call that 3, okay? And then I'm going to copy and paste that and take this to this arrow here. I'm going to call that, excuse me, beg your pardon. I'm going to call that 4. Okay. So we can see that a little bit more clearly. Let's go back to the question. It does say that the angle of contact for both the pulleys is 180 degrees, and the coefficient of friction, and this usually occurs between the belt and the pulley, is given as 0.24. Now, we will be using, I'm not sure you have done belts and drive systems, but you probably would at some point. And there is a relationship between the tension, the tensions of the belts that go across the pulley and the angle of contact of the pulleys with the coefficient of friction. I will give you that relation shortly. And that's what we will use to determine the torques. Okay, I mean the torque at both points, but also the tension. So the question now says we should determine the suitable diameter for a solid shaft, right? And if the allowing working stresses of 63 megapascals are there in tension and 42 megapascals in shear for the material. Okay. So we have to determine the suitable diameter for a solid shaft. So that tells us which equations to use. Okay. and we are given the maximum allowable working stresses, normal stresses in tension, okay, and the maximum allowable shear stresses of the material of the shaft. So this is going to be our sigma, okay, and this is going to be our tau, and we are to assume that the torque on one pulley is equal to that on the other pulley. Okay, so does our diagram have everything that we need? No, it doesn't. I'm going to zoom out a bit so that we can see one or two things. I hope that this is clear enough. What I will do now, I don't need this arrow anymore. You do understand what it was for. I will select all these guys, or them. It's not like going to do that. So let me select them one by one and group them so that this, that, this as well, this, yes, that, all of those guys, I group them into one. Okay, so let's see. Yes, everything moves together. Excellent. So I'm going to now move this. Let's move it a little bit that way, and together with this. Okay, we had that as one, but we haven't grouped this with it. So let's go for now. Keep grouping, and if you like, we can now group this too also. All right, so we can move this whole unit together upwards so that we can find space down here for what we need to do. Great. Now I'm going to get more lines. So yeah, we just need a vertical line that comes all the way down. Okay, this should be 0. Right, move it a little bit. Good. Control copy and paste, and I will move you this way. Okay. All right. And then so what I'm doing, remember in the last video I told you that we will not necessarily need to find out what the stresses are in every segment of this shaft. There are critical points that we will concentrate on. Now in this shaft there are 4 critical points. The first is this bearing here, the second is this bearing, right? And then we have this pulley and that pulley on those sides. So these are the critical moments. In fact, I would love to label them. Let me label them so it's easy to refer to them, because we are going to find, because we are dealing with bending moments, we will need to find the forces that are acting at those points. This looks quite small. Let me see if I could okay. Can we increase the size? Let's make it 18. Okay. See, I think that's a lot clearer for the purposes of this class or this video. So I'm just increasing the font size so that they can be seen better. That will also make 18. Oh my lord, I made it 128 instead of 18. There we go. Okay, so now I do the same to this guy. And then subsequently we have okay, so we would call, let's call that point A, right? And I will copy and paste and take it to the other side. It's a bit slow, it's getting sluggish. We'll call that B. Okay, for the point where the pulleys are, I'll call this bigger pulley, the 600 millimeter diameter pulley, I'll call it C. Okay, and I will call this one D. Okay, I will call that one B. Good. So it's easy for us to identify where what is. Great. So point A is a critical point. Point B is a critical point. Those are the bearings. This is where the bearings are. And you would note that when we're dealing with bending moment diagrams, even bending moments, the bending moments at these points, the bearings, which are the supports, they will all be 0. So the 2 points where we're going to check is point C and point D to find out whether the maximum bending moment acts here or here. And then we take that value and use it in our calculations, right? Now, I'm still going to need U, so let's do it this way. Too much, around too much. Good. Copy, paste, and why are you changing when I haven't changed it? Okay, now there we are with that. I think subsequently, because I will not have the luxury of editing this video before it comes up, so you're seeing all my processes, it's going to be a little bit delayed. I think I may be pausing it when I'm doing all the drawing tasks so that you don't waste your time seeing me moving lines around. Okay, so we've got this now, and then we know that the distance between C and D, we can find that out. Okay, we were told that the distance between A and B is 1 meter, that's 1,000 millimeters. Between A and C is 300 millimeters. Okay, the question did say that. And then between D and B, it's 200. So you have 300 this way, 200 this way, that's 500, right? And so what's in the middle should be another 500. Immediately you see that the position of my point C is grossly it's not very accurate. So I'm going to move it like so. Okay, just to let the visual appearance look as though that's 300 and that's 2 and that's 5. Okay, so I'm going to put those dimensions there now so you can see the distance between them. So here we have our dimensions. The 600 millimeter diameter pulley, as is illustrated here. 600 millimeters is the bigger one, the green one, right? And is 300 millimeters to the right of the left hand pulley. Okay, and we have the, what's that in there? Oh, no, that's not what I wanted to. Okay, it's fine. I don't know what that is. Sorry about that. I'm just trying to get this thing straight. And then the distance between both pulleys is 1,000 meters, and then the distance of the pulley at point B from the right hand bearing is 200 millimeters. Okay, so the distance CD is automatically 500 if you do the math. Okay, so with these, let's first see what has been given to us. Okay, every other, I think all the dimensions we've taken note of this is on the image we've drawn, so we will not extract that. We've taken note of this, but we may write this so that it easily goes into our calculations. And then we'll call this pulley 1. Okay, and the other one pulley 2. This is taken care of. We will not extract that. We'll take care of this tension. We know what that tension is. We will take care of this 400. So let's start. What have we been given? So I need to move to the next page now. Oh, and I carried you with me. Control Z. I need to group you guys with the last one. So select you and you and you and you and you. How do I get in touch with? Oh, good. That one before you. That or that. This and this. And then we put that, this, and this, right? And then every, oh dear me, what did you do, son? That's what I wanted to select. Let's go again. So that they are all selected now. So I will right click and group all of them. Okay, that's good for me. So I want this on the new page, and this new page I want you to be in portraits. All right, so what have we been given? Given the first thing that we were given was, let's go one by one. Taking that one, we can take this one as the diameter of the shaft of pulley, rather. So we'll say diameter 1 as diameter of the pulley is 600 millimeters. 600 millimeters. Okay. Diameter 2. Okay. Let's take diameter 2 before I come back to tension 1. Diameter 2 is 400 millimeters. Diameter 2 is 400 millimeters. Okay. Next in tension 1 is 2.25 kilonewtons, which is 2,250 newtons, right? We can bring this down like so. What else are we given? Checking that, we've checking this, we've checking that, and that already on the diagram. This as well. The angle of contact, the angle of contact, that is theta, is 180 and mu is 0.24. So theta is 180 degree, 180 degrees. Mu is 0.24. All of these are given in the question, right? So you see us writing this, we're just extracting the information that has been given, right? And then the maximum allowable shear stress, this sigma B is 63 megapascals and tau is 42. So this is very straightforward, right? Sigma underscore B is I've not forgotten the value. 63 was it? 63 and 42. 63 megapascals, and our tau will be 42 MPa. Okay. So these are the things that we have been given. Now, what did the question ask us to do? Remember, they have asked us to determine the suitable diameter for a solid shaft. So the questions we're using are for a solid shaft. Now, because we have both, this is a case of both bending moments acting and torsional moments acting. Okay, we know the equations we're going to use. So we're using two theories. Okay, we are, where am I? We are going to use two theories here to determine this thing. So two theories to be applied. Okay, and then we'll select which of them is the biggest, gives us the biggest diameter, and then we'll work with that. We have the Guest's theory, which is the maximum shear stress theory, and the Rankine's theory. Okay, those are the two. So what's the equation for the Guest's theory? Okay, it says that the it says that the equivalent torsional moment can be found by the square root of, okay, the maximum bending moment in the shaft plus the square of that, okay, and that is the same as, oh yeah, where did you run to? Give me a minute. And that is the same as supposed to be in here, as pi divided by 16 times, scroll so you can see what I'm doing, times sigma B, okay, oh sorry, this is not bending, this is shear, times tau, okay, times, oh, I thought I was in there, times d cubed. All right, so this is the Rankine's theory. So maybe I should just actually put this under here so that we are not confused as to which is which. That's what we need to That's what we need to find. And then as for that's the guests theory. As for the Rankine's theory, we have that the equivalent bending moment, right? Which is, M underscore E is found by this, we will say half, and we're finding M plus the square root, okay? The square root of M squared plus T squared. Okay, all of that will equal pi divided by 32 times sigma b, sigma underscore b times d cubed. I think I should make this smaller so it all fits in there. Why don't you become 20 for me? Good. So these are the two theories we will apply, and our aim is to determine this value. So we will start with the guests theory and walk through them. And so number one, okay, so we can just make a statement using the guest theory. I remember I said this theory is the same thing as the maximum shear stress theory, right? Okay, so when you look at this, let's ask ourselves, let's follow where to find D. For us to find the value of D, since we have only one equation, we must know all the other parameters there. Okay, do we know tau? Yes, tau is given right there. Pi is a number, we know pi. 16 is a number, we know 16. The torque transmitted, do we know the value of the torque? It's not been given directly, but we're dealing with pulleys, right? And so we can find the torque. We know an equation, okay? Maybe I should, before this statement should say, we first find D using the guest theory, okay? So we're about doing that. But the torque here, how do we find it? Now, since we're dealing with belt drives, there was an equation I'd given us earlier. That the torque, okay, at a particular pulley, that rotates a particular pulley, is given as this. Is given as a product of the difference in the tensions of the tight and the slack sides of the belt multiplied by the radius, okay, multiplied by the radius of that distance. So here we can find, so if we know T1, T2, R, we can find T, okay? So we know R because R, and by the way, R here is R1 because there are two pulleys, okay? This particular pulley, let's assume the one that has the first, so let's come back here so that you're not thinking I'm dealing with arbitrary terms. The pulley that has T1 and T2 is this pulley here, the first one, where we have said its diameter is D1, 600 millimeters, right? So that should be R1. So we know R1, we know T1, the first, the maximum tension in the belt has been given us, that the tension in the tight side. So we are meant to find the tension in the slack side. So in this equation, there are two unknowns. For me to find this, I must find this. So I now need another equation that will enable me find T2 if I know T1. And looking at what I've been given the angle of contact, and I've been given the coefficient of friction. So there is an equation that equates that. I'll come to that shortly. So if I find T2, that means I can find T. Okay, so let's go back to Guess theory. And then the next thing I need to find is where the maximum bending moments are. For that one, I would need to find all the forces. I'll need to define all the forces acting on the shaft and where they are acting, and then find the bending moments at the critical point. Okay, then I will find what the maximum bending moments are. The peculiarity with this question is that I have got forces acting in two directions. In the horizontal direction, oh, that's what we're showing. I don't remember that comment. In the horizontal direction, that's T3 and T4. And in the vertical direction, that's T1 and T2. Okay, T1 and T2 act at point C. So at point C, there is a force that is pulling, okay? It is pulling down this shaft at this point. At point C, there is a force that is pulling the shaft away from us into the screen, okay? Because if you look at it at this from the end, the directions of this. So at point C, there are vertical forces acting, no horizontal forces. At point B, there are horizontal forces acting, no vertical forces. So we are constrained to split this problem into two. We deal with the vertical forces. As a consequence of these vertical forces, we have vertical reactions at point A and B. Then as a consequence of the horizontal forces at point B, there will be horizontal reactions at point A and point B. Okay, so we'll split them up into those two sections. We will find the values of those reaction forces, and then we'll find what the bending moments are at point C and point B, which are the critical points. Then we will consider the horizontal one, find out the horizontal reactions that are developed at point A and B. And then we'll also now find out, as a consequence of those forces, the bending moments at point C and point B in the horizontal direction. We'll be using the subscripts V to represent vertical direction and H to represent horizontal direction. Then when we finish, we will now take the equivalent, or we will find the sum, vector sum of those two forces. Okay, the horizontal, of those two bending moments, the horizontal and the vertical, to determine what the maximum bending moments are. You will see as we will do it. Then only then can we come back to this equation and impute the values and so. Once we do that and we're able to find the value of D, when we come to the Rankine's theory, it's going to be straightforward, because we would have known what M is and would have evaluated this guy already. Okay, and then pi is a number, 32 is a number. We are given sigma B, and then we are going to find D3 thereafter. So follow me very, very carefully as I think through the problem. So first off, we are starting with the Rankine's theory. So I'm off to find what the value of T is. Then after that, I will now find what the value of M is, and I come back to this equation right there. Okay, so we know this. Okay, we know what R1 is. We know this T1, the maximum tension, the tension in the tight side. Now I need to find the tension in the slack side. And now I know that there's an equation that says that if we find 2.3 times the log of this number, okay, T1 divided by T2, right? This expression is the same thing as the product of the coefficient of friction and the angle of contact of the bearing. This is another equation used in belt drives. So let's look at this equation that I've provided now. We know theta. Okay, theta has been given to us as 180. degrees, right? We know now when we come to use that, this equation here is given to us in radians. This angle here is in radians, not degrees. So we need to convert 180 to radians, right? And that's quite straightforward. 180 is the same thing as pi radians, okay? So we might as well put that here, knowing that this is pi in radians. Or just write, well, just say pi. We know what that means. It's in radians, because I don't want it to drop down. Okay. And then we know mu or mu. You see, the way your teacher, your foundations on how you pronounce things are very much dependent on who taught you. My secondary school physics teacher will call this mu, even though the spelling is mu. I honestly don't know what the correct pronunciation is, but over the years I've stopped calling it mu, even though it's spelled mu. It's a Greek letter, by the way. So that's mu or mu, however you decide to call it. We know the value, and we know what the tension in the tight side is, T1. We don't know T2. Logarithm is an operation. 2.3 is the number. So we can find what T2 is, right? We can do that. So how do we do that? We will divide both sides. So I'm trying to make T2 the substitute form. If I divide both sides by 2.3, then I'm left here with the log of this number equals that. So what I'm saying is this, that I will end up having T underscore 1 divided by T underscore 2 as the T1 over T2 equals mu what is wrong with you? Was mu times theta divided by 2.3, right? That's what, oh my, this is the log, not just this guy, right? So here we would need to put a bracket around it, okay? And in front of that, that will be the log of it, okay? But since I'm looking for T2, T1 over T2 is a ratio that is locked inside the log. If I want to do away with this log, then I find the antilog of both of these sides, right? So let me just go back to where I was. So we can still work with this, but we assume that we have dealt with the log by taking it to the other side, and the way to do that is to find the anti-log of that number. When we do, then it means that T2, okay, if we cross multiply, T2 will be T1 divided by this whole guy here. So it follows that T underscore 2 is going to be T underscore 1 divided by anti-log. Let's do it that way, and then we'll come back down here and get the anti-log. So what's the anti-log that we're looking for? It's this number. So I'm going to copy that number and I'm going to put it right there. Okay, so we can now find what T2 is. Okay, so let's evaluate this and see. Let's evaluate this guy and see what he gives us. So what's T2? T2 is 2250 in newtons divided by 0.24, that's mu, 0.24 times pi, okay? Because, oh, scare me. I think I should check off this, no, I think you'll be able to see. Times pi, right? Divided by 2.3. So everything there is a number, okay? This is not a live class, otherwise I would have allowed you to calculate and let me know, but this isn't. So I will just get the value for you. Approximately T2 will be 1058 newtons, okay? 1058 meters. That's going to be the value of C2 when you run that math. Please verify that you have that value. So now we know T1, T2, okay? And so we can find the value for the torque that is acting at that point. But before we get excited and run away, we will need to find T3 and T4 too. Since we're here, let's find it. Otherwise, we are done with finding, we could have easily found what the torque is now. But let's persist a bit, okay? Let's persist a bit and also find T3 and T4. But before doing that, let's find T, okay? What's the torque? Excuse me. What's the torque? So let's copy that and come down here. Now we can find the torque. We put that there, and the torque therefore is now this guy, which will be what's T1? T1 is 2250. Okay. I should have put that in the bracket. Okay, so let's put this in the bracket. 2250 minus 1058, right? Multiplied by R. Okay, and then R is going to be what's the value for R? It's 600 millimeters, right? Divided by 2. Okay, 600 millimeters, because we're dealing with radius and not diameter. So that's 300 millimeters or 0.3 meters. So our torque is in Newton meters. So this is times 0.3. Okay. And when you do that math, the value you have for your torque is, where is the value that I've worked on? Okay. The value you have for the torque, maybe this should come under, will be 357.6 Newton meters. Okay, that's the value for the torque. Excellent. So now that we know the value for the torque, since both pulleys are on the same shaft, we assume that they're subjected, well, let's not just assume anyhow. Or if you look at the last sentence, it says, assume that the torque on one pulley is equal to that on the other pulley. So with that statement, it means that the torque that we found for the pulley at point C, which is a 600 millimeter diameter pulley, is the same as the torque acting on the pulley at point D, which is the 400 millimeter diameter pulley. So this same equation works. It's only that this time around, where are we? This time around, we can say that, and here we'll say also, T, that same torque, is the same as T3 minus T4 times R2, where R2 is the radius of the pulley at point D. So we now know this torque, we now know this R, but we don't know any of these two guys. They were not given to us. But also remember this equation, right? There's an equation that exists here. Let's copy it. Okay. That says that come a minute. Yeah, the equation that exists there that says that 2.3 times the logarithm of the ratio between the tight. Now this time around we are going to use T3, that's the tight side, and T4 will give us that value. Okay, and so the expression we had here, we also have that same calculation as we had before. Remember that everything on the right hand side is the same as was before. The only difference is This time around, that's the ratio of the tight side of the second pulley, which is T3 divided by, or 2, the tension in the slack side, T4. And this, and if you did that math, that value is 2.127, 2.127. That's the value. Now, what that means is simply that that means that, or I can still do it here. It follows that my T3 is 2.127 times my T4. I put the times there to make that look a little bit more beautiful. Oh no, that's not. Oops. There we go. Okay. So I can take this and put back in this equation, and then that will make me have just one unknown. All right. So wherever I see T3, I'm going to put this value here. So if I pick this now and I bring him down here, okay. Remember, so wherever I see T3, this is the guy that is going in there. Copy this and put him there. That's T3. Okay. So I have 2 times this minus 1 times of the same value. So it's going to be 2.127 minus 1. That will be 1.127 T4. So by this, we can say that maybe just for the sake of this, if we divide both sides by R2, we would, since I'm taking this step by step, let's do that without jumping steps. That means that this guy is the same thing as T1 divided by R2. Okay, from here, divide both sides by R2, right? And this minus this will give us 1.127 T4. Okay, I hope you are all following me. Okay, so let's so what we're saying is 1.127 T4 is the same as, oh, was that T1? That's not T1, that is just the torque. I beg your pardon. That is just the torque right there. Okay, given by the torque divided by R2. Okay, now if we again divide both sides by this value here can vanish, and it will appear here as 1.127 times R2. So that's what T4 will be. So if we put in the values of the torque that we found, the torque was 357.6 Newton meters divided by R2. R2 is, that's 400 millimeters, that's diameter, divided by 2, that's 200 millimeter, which is 0.2 meters. When you do that math, you will find that your T4 is 1,588 newtons. Okay, so now that we know what our T4 is, we can find our T3 using this equation right here. Okay, so we now know what T4 is. So we come here and we are saying that T3 is 2.127 times this value, which is 1588. Okay, and this gives us an approximate value of 3376 newtons. Okay, So we found all of those guys. Now that, so don't forget that what we're trying to do is to use the guest's theory to find the diameter of the shaft. This is what I'm finding. So I need to know this. That's given to me. These are numbers. I know them. I've just found this. So the next thing we need to do is to find this value. And to find this value, we must find all the forces acting here. Okay. And because of my time, what I will do will be to I will just use notations. I will not come to my diagram to draw or say a few things, but just follow me. Follow me very, very carefully. I would have come here to draw my bending moment diagram. Maybe I may come back here just to illustrate one or two things, but just keep it at the back of your mind what we are doing. I had said earlier that because we have these forces acting in these two orthogonal directions, we're going to split and consider the vertical direction first, then the horizontal direction second, and then we amalgamate them. We take the vector sum of them to find the resultant bending moment acting in the shaft at the critical points, point C and point D. So the forces acting at point C, what should we call them? Let's call them FC. So we now find all the forces acting on the shaft. So we could determine the bending moments at the critical points in the shaft. Okay, that's what we want to do. So to do that, at point C, follow me carefully. At point C, let's scroll up to point C and see what's happening there. At point C, this pulley here is delivering power or torque to another pulley vertically downwards. Below it, that's the direction of T1 and T2. So the forces acting at point C is the summation of T1 and T2. T1 and T2 are both pulling down the shaft at point C. Okay. So let's note what happens at point C. At point C, I'm going to use F to represent the forces, the vertical forces. Vertical forces at point F are given as a sum, of the tensions, okay, acting at that point. So what are T1 and T2? Let's get them. I'm plugging directly. We had found them before. 2250 and 1058. So this is 2250 and 1058. Oh dear me. Okay, I'll just cut that out. And that's where we're going. And that value is, when we sum these two guys together, we're going to have 33,308 newtons. Okay, that's FV at point C. Now, similarly, at the same point C, FH, the horizontal forces are 0 because there are no forces that act in the horizontal direction at point C. How about the back of your minds? And then I will probably come back to point C to, well, let's go. At point D, all right, the vertical forces, oh my lord, the vertical forces that are acting at point D are 0. Okay, why did we say that? Because when you look at point D is being driven by a motor that is to the right of it, horizontal. That's where T3 and T4 are. So there are no vertical forces. However, there are horizontal forces. And so whilst the vertical forces are 0, we can find or deduce or determine the horizontal forces like so. This will be the sum of the tension in the tight side of that pulley and the tension in the slack side, that's T3 plus T4. And what are the values of T3 and T4? They are 3376, the value of T3, plus 1588, and the value in the slack side. So altogether we have 4964 newtons as the horizontal force acting at point D. Now we need to now find 4 sets of reaction forces. So the bearings A and B are going to react to the forces that are in the vertical direction and the forces in the horizontal direction. So we need to find, these guys. Which guys are we finding? We're finding the reactions at point A, in the horizontal direction. We need to find the reactions at point A again in the vertical direction. We also need to find the reactions at point B in the horizontal direction and the reactions at point B in the vertical direction. All right, so we can do all the verticals first and then all the horizontal next. So if you like, we could move these guys away from here and bring this one here. Okay. Good. So those are the guys that we need to find. Vertical. How did I do it? I think it should just be H like this. That's better than this. Oh, well, I didn't know that was together. What have I done? Okay, let's do this again. R underscore BH, comma, R underscore AH. That's what we're looking for. Fine. So let's start with the verticals. Let's get back to our diagram so we understand what's going on. So we will take the notation that all forces acting vertically upwards are positive and all forces acting vertically downwards are negative. We have a single force acting at point C, FV, and it acts downwards. The value of that force at point C is 3308 newtons. That's 3,308 newtons. That's the only force acting vertically downwards in this whole arrangement. Now, the reactions or the bearings at point A and B will provide a reaction to that force. Okay, so there's going to be a vertical opposing force at point A and a vertical opposing force at point B. If this point of action of point C, or if the pulley were bang on in the middle, at the midpoint of this shaft between these two bearings, then the values of A and B would have simply been to divide that, since it's a single force, right, to divide it into two equal parts. But since it's closer to point C, okay, the reaction at point A will be more than the reaction at point B. However, we still hold true that FV, we can write this, and this is due to using the equilibrium equation. So don't forget, so using the equilibrium equations, right? Using the equilibrium equations, which are these are the equilibrium equations, that the summation of, where is my summation? Yeah, steno shortcut for you. No, the summation of all the forces acting on this system is 0. Okay, and we also hold true that the summation of the bending moments, okay, on that body will also be 0. So that's where we're going to apply all these total upward forces equals total downward forces, total forces acting to the right equals total forces acting to the left. And on the basis of that, we can now say that this vertical force that we now know and have found at point C, remember there is none at point D, that's why we're not considering it. This equals the reaction at point A in the vertical direction plus the reaction at point B in the vertical direction. All right. So that will mean, if we rewrite this equation properly, that will mean that RA V plus RBV will equal 3308, what's that value? 3308 newtons. Okay. Now, we will now take the moments of this vertical force about any of these other points so that we can eliminate that force. So if I'm going to take moments, so I need you to note, maybe I should draw so that you will not anyway. At point A, there is a reaction force, insert shapes. Excuse me. There is a reaction force that is acting upwards. Okay. I'm going to make that shape red. I want it a little bit thicker. Wait. Let's use 3. And we're going to copy and paste. And this is also what's happening at point oh, not there yet. Where are you going, son? Okay, there we go. This will be, if I would label that, I will label that R. Let's come down here, path. So this will be R underscore AV. Okay. Let's make it a little bit bigger inside so we can see. Excellent. That's, and then there, I want to copy and paste. Then I can have it on this side, but the one on this side is RB because that's what's there. So RB. Good. There we go. So we can take the moments about any of these points. So let's take the moments about point A. Okay. If we take moments about point A, remember that this force is acting vertically downwards. And if I'm taking moments about this point, it will be a clockwise moment. Be clockwise. Clockwise. If I'm taking moments of RB about this, it will be what? Anti-clockwise. So the moments of this must equal the moments of that. So clockwise moments will equal anti-clockwise moments. So keep that at the back of your mind and note that the distance between RBV and RAV is 1,000 millimeters, right? The distance between FV acting at point C, maybe I should have called that FCV so that we don't confuse it. Okay, I think that's what we need to do, because at point C, we call that FCV, right? And then FCH is 0. Then when we come to point D, that will be FDV, that will be 0, and FDH will be 4964. So we could easily differentiate them. So this is C. This here is FCV that is giving us these values that we are now working with, right? So taking moments about point A, okay, will give us this, that FCV times the distance between FCV and that guy is 0.3 meters, right? Will be the same thing as RBV times 1. Okay, that's us taking moments about that. And obviously, we know what FCV is, right? Aha. So RBV then, the reaction, vertical reaction at point B is therefore 3308 times, what's the value of that number there? 0.3. Okay. So the value that we have, where is my calculation? The value that we have is that RBV is 992.4 newtons. Okay, so RBV is, it's 992.4 in newtons. So we found RBV. Okay, so now that we found RBV, it's easy to find RAV. Okay, so let's go ahead and find RAV from this equation. Okay. We can make RAV the subject of formula by saying that it is F. So don't mind how I'm doing this, but it's correct. You can check it out later. Okay, it's going to be Control Z. Don't put it in that's outside. Yeah, so we can easily select this here minus. Okay, so that's your RAV. Your RAV will be the value of FCB minus the value that we just found out. And so that's going to be 3308 newtons minus 992.4 newtons. And so the reaction at point A acting vertically upwards is going to be 2315.6 newtons. Okay, that's going to be our RAV. Now, this is for the vertical side. We found the reactions in the vertical direction. We might as well now find the bending moments. Follow me very, very, very carefully. Okay, let's find the bending moments. Or maybe we should know. Let's go on. I beg your pardon. Sorry. Let's go and find what the values of them. RAV, so we need to find these. We found AV and BV. Now we need to find AH and BH. So for AH and BH, okay, we can say that the force acting at point B in the horizontal direction will be the sum of the reaction forces to it. So when this one is acting to the right, the reaction forces at point A and point B are acting to the left. Okay, so let's go back to that diagram so you have a grasp of what we're saying. We're saying that because the tension T3 and T4 tend to pull this shaft to the right, the bearings at point A and B will resist that pull by acting towards the left with certain amount of forces. And the reaction at point B will be significantly higher than that at point A because the pulley at point D is closer to B than A. And you could have seen that also how that the reaction for the vertical one, because the pulley is closer to A than B, where are the values? RA is bigger than RB. Okay, so in this case also, we know that the reaction at point A acting in the horizontal direction plus the reaction at point B acting in the horizontal direction will be the same magnitude as the value of the horizontal force at point D. And this is only because the horizontal force at point C is 0. We have noted that earlier. Okay, so again, we apply the same principle that for us to find one of these, we need to take moments about one of them. Okay, so let's take moments about B now. And we're choosing that strategically because FDH is closer, it's acting closer to B. So taking moments about point B. By the way, you can take moments about point A, any point at all, you will still arrive at the same answer. So taking moments about B, what that looks like is this. If I'm taking moments about point B here, because RBV acts at point V, it will have no effect, and so that moment will vanish, and so will that force. But this force is acting to the right, okay, to the right. So if you look at it, just assume for the benefit of the doubt that right is up, okay. If you're looking at that at the top, right is up and then left is down. So if this is going that way and we're taking moments about point B, it's going clockwise, right? Then if you take what's it called now? The moments of this point at point D here, it will be in the opposite direction because this is acting downwards. Don't get confused with V. We're not dealing with V. That's why I say assume, because this pulley here, if I'm looking at the top, let's assume that we're looking at this guy from the top, not at the side as this current one is. So T3 and T4, their combined effect will be in that direction, right? And the reactions here will be downwards. So while this is going this way, this one is going the other direction. So the moments of FDH about P will be equals to the moment of RAH about B. Okay, and we've had those distances already. Okay, so let's do this very quickly. So taking moments about that, it means that FDH, okay, times the distance between these two guys is 0.2 meters. It should be the same thing as the radius. I say radius, I beg your pardon. The reaction force at point A in the horizontal direction times the distance in meters to point B, which is 1. Okay. So again, we can easily find what can easily find what RAH is, because RAH times 1 is RAH. The value of FDH, which is where's my FDH? FDH is 4964. FDH is 4964. So this is 4964 newtons times 0.2. Okay, and what would this value be? Okay, let me quickly work that out, because I had taken moments about A the other time. So give us the same thing. Just give me a minute. Okay. Yeah. So what we have is approximately RAH is 992.8 in newtons, okay, which is approximately 993. Leave it that way. And then we can now take this value and put in this equation here, okay, and then we will be able to now find RBH. So we are looking for RBH now. So RBH will be putting it on that side. It will be FDH minus, okay, minus RAH. So what's my FDH? It is 4964, and out of that we are taking 992.8 to give us 4964. Okay, that gives us 3 FD. Let me be sure it was my F 4964. That's correct. So this will give me 3971.2. Okay, 3971.2 newtons. Great. So that's the value of your RBH. So you can see that's significantly higher than this. So now that we have known all these values, we can now find what the vertical the moments at points C and D are as a consequence of the all the forces acting in the horizontal direction first, and then in the vertical direction, and then we take the so let's go. So we now find the bending moment. That's what we're looking for. We're looking for the maximum bending moment at the critical points C and D. Okay, we now find the bending moment at the critical points and determine which of them is the highest or the biggest. What should that English be? So we know from what I've taught you previously that since the reaction forces are at point A and point B, there's going to be no bending moment, and since they are the extremities of your shaft, there's going to be no bending moments at those points. Those are the support points. But wherever they are, that will be the support point. So there's no deflection. There's no bending moment. So we automatically know that the bending moment at point A in the vertical direction is the same as the bending moment at point B in the vertical direction, and they're all what? They're all 0 now. So this is us finding vertical first. So at point C, we can find the bending moment at point C. So if you look at point C, let's get to point C. Here, what is the bending moment at point C due to the vertical forces? This is RAV. This is acting in the, what's it called now? This is acting in the clockwise direction. So if you are coming from the right to the left at point C, your bending moment will be RAV times 300. Please know that. Please know that. You can also find the bending moments at this point by going to point, what's it called? By going to point B and saying the bending moment at point C is the reaction forces at point B, RBV, times the distance from that to here, which would have been 700. So we just use RAB times that, just point C. So if we come from the left-hand side, the bending moment at point C will be like so. M bending moment at point C, but this is the vertical one, is going to be given as the reaction forces at point A in vertical direction times 0.3. And we know that the reaction forces at point A that we found were 2315.6 times 0.3, right? And that value will give us 694.7 Newton meter. Probably should come down so that made no difference. That's fine. Okay. Now at point D, at point B, this is vertical now. We know that the bending moment at point B in the vertical direction is going to be the same time. So we are going to be a little bit smart here. If we are going to come from the right hand side in finding the bending moments at point B, we have two forces to contend with. We have RAV and then we have FCV. Okay, both with their various distances. This is going clockwise, so it will be positive. This is going anti-clockwise, it will be negative. That's a lot of calculation. That value is the same thing as what's happening on the right-hand side. So which is RBV times this distance alone. So that's what we're going to work with. Okay, I'm going to say that the bending moment at point C in the vertical direction is the reaction forces at point B in the vertical direction times the distance between them, which is 0.2. Okay, and what was our RBV? What was our RB? The RBV was 992.4, right? 992.4 was the RBV. Now multiply that by 0.2, and that gives us 198.5 Newton meters. Okay, great. It's looking good so far. Now do note that each of these are very simple in themselves if you have gained the understanding of bending moments, where they act and all of that. That's why I'm taking my time to explain. I'm not saying certain things now because I said them in the last video. Okay, so if you want to, there are certain things you're not understanding why things are the way we are saying them, check the last video and you will understand. Okay, so we are finished with the vertical distance. So we also know that if we, so maybe I should have put a heading here. In vertical direction, okay, now we are in the horizontal direction. Okay, we know that the bending moments at point A in the horizontal direction is the same as the bending moment at point B in the horizontal direction, and both of those guys as 0, 0, right? So at point C, what will be the bending moment, right? So M underscore CH, now this is the horizontal component of it, will be, so let's come back to point C. And after this, I'll be coming back to the diagram because you should get a hang of it. So at point C, the force, this thing will be the reaction at point A in the horizontal direction. So RAH times 0.3 will be the value of that. So it's going to be RAH times 0.3. That's going to give you the value of the bending moment at point C in the horizontal direction. Okay. What is our RAH? Our RAH was 992.8, right? We are, oh Lord. Give me a minute. Okay, that's still looking for me. Thank you. And thank you. So times 0.3, right? So what's that value? Give me a sec, this calculation. This is 992.8 times 0.3. Okay, and that gives me 297.84. This gives me 297.84 in Newton meters, right? And at point B, we're just going to use the same principle. And the bending moment at point D in the horizontal direction is the reaction forces at point B, this time around the horizontal direction, times 0.2. Okay, well, being a bit smart there. So this will be 3971.2. That's what we had, times 0.2, and that value will be, I'm dealing with 3971.2 times 0.2. Okay, and the value is 794.24. Okay, so this equals 794.24 Newton meter. Great, so we found the bending moment at this point. Now the question is this: what then will be the bending moment at point C, and what will be the bending moment at point B? These two guys will be able to find, I mean, between the two of them, they will have the highest value. Okay, that's the value that we will now take and put in our guessed equation to find the diameter. Okay, so to find the resultant bending moment, this is the overall, right? At point C, at point C, MC now. Sorry, I beg your pardon. M_C will be the square root. So if we're going to take the vector sum of that, magnitude of that will be the square root of the bending moments at point C in vertical direction squared, right? Plus the bending moments at point D, sorry, at point C in the horizontal direction squared. Okay, that's how you do that. So what are those values? We're going to pick them and plug them here and see what they give us. Okay, what is MCV? MCV 694.7, and MCH is 297.84. So we're putting that value here was saying 694.7, square that, okay, square that, and then add that to the square of 297.84, okay, squared. All right. When you do that, you will find that the value of the bending moment at point C is approximately 756 Newton meters. All right. So let's find the one at point D and see which is bigger. At point D, I should have a comma there. At point D, the bending moment at point D is the square root. So this same thing that we have here, I'm just going to copy all of that and edit. Okay, save our time. It's going to be D instead of C. Wherever you see C here, that's actually D. So the bending moment at point D in the vertical direction squared plus the bending moment at point D in the horizontal direction squared. We sum that together and take the square root. So MD, the MDH is 198.5. I think that's what we had there. And this one here, MDH is 794.24, okay, squared, and that gives us 819 approximately 0.2 Newton meter. So when we look at this, follow me now. We are where we wanted to be. Okay. When we look at this, between these two at MC and MD, the maximum, the bigger of them is 819.2 Newton meter. And so we say that that's the maximum bending moment acting in this shaft. And so we use that point. So the diameter of the shaft we're calculating is for point D, because that's where the maximum bending moment acts. Once we get that right, if we use that same diameter or more anywhere on this shaft, we are certain that it will not fail, because the bending moment at D is lesser. The bending moment at A and B are completely zero, right? So the maximum bending moment at that point. Now we can go back to the Rankine, to the Guest theory or the maximum shear stress theory, and find what the value of the diameter should be. Since we already know tau, we're able to find what T is, and we have just also now determined the maximum value of this. So I'm going to copy this because we're using that equation now, and I'm going to go right back down to the bottom where we were. And yeah, so now the maximum bending moment is what? Is push maximum at point D, and is what's the value? 819.2 Newton meter. Okay, so what that means is that M is that value, 819.2 Newton meter. Okay, so back to the Guest's theory that says this. Okay, and so we can first find the equivalent value, because we'll need this later. Okay, let's copy you like so. Copy. Do you remember what the value of our torque was? Let's come find our torque, and we'll come back. A bending moment is there already. the torque T was, where are you? Here, 357.6. 357.6. So what that means is M here is 819.2 squared, and the torque here is 357.6 squared. When you do this, you would find that your equivalent torsional moment is 894 Newton meter, which we can write as 894 times 10 raised to power 3 Newton millimeter. Okay, we're doing that selfishly so that when we do our calculation, our diameter will be in millimeters. Okay, so now that we have that, we will go ahead and make D the subject of the formula. I think I've done that at some point before in this, so I'm going to just find it somewhere and copy it to save my time. How far back do I need to go? Hopefully not too far. Here we go. Okay, this is depending on it. Where is the further down? Yeah, there we go. This is the value of T. Select everything, and we get right down to the bottom. Okay, so now D is given by this. We know everything here. We know what our TE is. We just found out. We know pi is a number, and we know tau. Tau was given to us as what? Tau was given to us as 42 megapascals. That's 42 Newton per millimeter squared. Okay, that's why we do not change that mega to 10 to the power 6, so that we can leave that millimeter value and our diameter of the millimeter. And so, if we're doing this, this equals the cube root. This equals the cube root of 16 times 894 exponent 3 times 10 to the power 3, times 10 to the power 3 divided by pi times 42 megapascals. Okay, when you do that math, you will arrive at the point where your D is, or your D is 47.6 millimeters. Now, this is according to the guest's theory. So we must now also go ahead and find out what the Rankine's theory says. So now I'm checking the Rankine's theory, which is this. I must go back up and grab it. Okay, excuse me. Excellent. This guy here, and the equivalent bending moment is given by all of that expression. Okay, this one. Now let's check. We have everything. This guy here is TE actually. Okay, this guy here is TE. That is M. And so we can easily find ME. So let's do that. Let's do that. We can say that ME, just that one, is actually half. I'll put you again. Is actually half of M plus TE. That's basically what ME is. And so if we sure you're already tired. Don't worry, we're rounding off and we'll stop at this point in this video and continue later. So ME here is going to be half. Okay, what's the value of our bending moment? So it's 819, that's the maximum bending moment, 0.2 plus the equivalent bending moment that we just found, which is 894 Newton meter, because that value is in Newton meter was so down. So that's 894 Newton meter, and that math will give us 856.6 Newton meter, or it is 856.6. Sorry, that there is 6.6 times 10 raised to the power 3 Newton millimeters. Great. And then we come back here and make D the subject of formula. That also is somewhere nearby. So I'll just go grab it right here. Okay. So I'll just copy the whole thing and edit accordingly. Okay, so now, so that's the value for D. If we make this the subject formula, so that's 32 times. In this case, our ME is 856.6, and our sigma B is 63. I believe it was 63 megapascals. When you do that math, you will arrive at this value that D is 51.7 millimeters. And so when you compare these two values, this is the one from the Rankine's equation, and this is the one from the Guest equation. Obviously, the Rankine's equation is higher. Okay, so we take the larger of the two values from the theories. Okay. Therefore, come on, son. Are you tired? Therefore, our D is 51. We adopt D as 51.7 millimeters. We select a standard sized shaft of diameter. What's the standard size of shafts above D? As 55. So 55 millimeters. Okay, and there we go. We have answered that particular question. Okay, it looks really long, isn't it? But it's pretty simple. You can go over the video to follow my thought process. So I took it step by step. Okay, thinking through each of the parts of the questions, thinking through every step, so that you could follow and learn how to approach questions like this. All right. Thank you very much. We will continue in the next class. For this question, the selected diameter is 55 millimeters. A solid shaft of size 55 millimeters will function safely under the conditions provided in the question. God bless you.